Hey everybody, we're back again. Day 2 of e-learning. Hopefully you got something out of yesterday's lesson on chemical stewardship. And today what we're going to do is focus a little bit more on what are those chemicals that we have to be careful of. And generally they're the things that are solutions. So on the calendar, you'll see there's a whole bunch of little background videos for you to watch. There's one titled, What Are the Solutions? The Basics. And it's a short video that you should probably watch, maybe even before you watch mine. Doesn't really matter the order. There's a few general notes on this page for you to kind of summarize everything we've done. You'll see that as we go through. Not sure if you took the time to look at the guy that ingested silver and turned blue. I included that video one more time just in case you didn't get to see it yesterday. And then we'll talk a little bit about properties of solutions and how emulsions are made, and that's what this video deals with. And then of course, if this were real class, you'd say, why don't we ever do a demo or lab? Well, we're going to do both today, right? So we've got here a demonstration of an oil absorbing polymer, and I'll let you you can watch that, and we can talk about it a little bit if you wish. And then finally, there's a lab you get to do, i.e. watch the video of somebody else doing it, how to make slimy gloop. And it is something you can actually make at home, and they'll kind of go through the recipe of how that's done as well. So let's see if we can get started now with what we want to be doing, which is our unit here on solvents. So hopefully it's all still recording and you're going to see this. So solvents, we've talked about like methyl ethyl ketone or water or turpentine. These are solvents, but what are they really? And let's delve into that. So these are all some organic solvents that you can deal with. Now, if you remember when we did our unit on molecular geometry, the real purpose of that was to understand that some substances are polar and some are non-polar. And then we learned a phrase, like dissolves like. And what that meant is a polar substance will dissolve a polar substance, and a non-polar substance will dissolve a non-polar substance. Perhaps you remember a story I told you in the first semester about a friend who had forgotten to change their oil in their car for several years. And somebody was trying to get the oil filter off and basically used a screwdriver to stab it and shredded the oil filter. And then it had no oil in the car. Where the oil filter was supposed to be was just shredded metal. And they called me up for help. And of course, what I did is I ran to school and I got a solvent that would dissolve oil. Now, do you happen to remember, is oil polar or non-polar? Propul? That's right. Oil is non-polar because water's polar, and we know oil and water don't mix. So I grabbed a non-polar solvent and I put it in a squirt bottle. I squirted it all around the stuck-on oil filter, waited a few seconds, cut a potato in half, stuck that on the shreds of metal and twisted off the oil filter, and voila, we had that car ready to go, filled up with oil after we put in a new oil filter. So my knowledge of chemistry actually helped me in the real world. Sometimes you say, when does this stuff ever work? Well, it does work once in a while, right? So there's a few definitions we need to know, and these will be important for you to know for the test or quiz if we take. So a solution by definition is always a homogeneous mixture. And let's break that word down. Mixture means it can have any ratio you want. If we think about salt water as a mixture, it can have 2% salt or 20% salt, and both can be mixed uniformly. The homogeneous or homogeneous means mixed uniformly. The opposite of homogeneous would be heterogeneous. If we think about a pizza, for example, a cheese pizza would be representative of a homogeneous mixture. Every bite you have of pizza is bread, sauce, and cheese. A pizza with the works is going to be a heterogeneous mixture. Each bite would be a little different. Sometimes you get sausage, sometimes you get pepperoni, sometimes you get, I don't know what they put in there, but whatever you order on your pizza, it's different every single bite. That would make it heterogeneous, okay? Now, mixtures are different than compounds. Remember, compounds have a fixed ratio of elements in them all the time. And an element, on the other hand, is a single type of atom. Okay? So elements are different than compounds, are different than mixtures, but all solutions are homogeneous mixtures. Now, when you make a solution, you have to dissolve something. Whatever you dissolve is called the solute, and whatever it dissolves in, we call the solvent. Another way to think about this is the solvent is whatever you have more of. It's the greater amount, and the solute is whatever you have less of. This statement, what the solute and the solvent are, determines whether a substance will dissolve and how much will dissolve. What this is really trying to tell us is that a polar solute will readily and easily dissolve in a polar solvent, but a polar solute will not dissolve appreciably into a non-polar solvent. So, in other words, like dissolves like. That's something that's important in chemistry to understand, that things that are similar will dissolve in one another based on polarity. Other factors that will determine how fast a solution will be made. Maybe you're sitting at home and the grocery stores have no food in it, and you're in a lockdown situation. You can't even get out of your house. So you go in the cupboards, and what do you find? You find maybe some ramen noodles. So you open up the package and you find some dry looking noodles and a little cube of salt. Well, you put the cube of salt in cold water and it just sits there. It's not going to do very much in cold water. So it says here, a substance dissolves faster if it's stirred or shaken. So of course you're probably stirring that water a little bit. Of course, if you read the directions, it said you should boil the water first. So if the temperature is increased, the water molecules will be moving faster at the molecular level, causing collisions between the solute, that's what's dissolved, and the solvent, and that's how things dissolve. And finally, if you were just to crush that little cube into smaller pieces, you get more collisions with the salt, that's what the little cube is, and the water. So some things that you can do to increase the rate of solution formation would be you can stir them, you can crush them, and you can raise the temperature. Now I would just throw in a little bit of a caveat here. If you raise the temperature of a gas in a liquid, a gas becomes less soluble. If you think about it, if you've got a fish tank at home, if the water gets too hot, what happens is the oxygen can't stay dissolved. It's much like if you boil a pan of water, the little bubbles you see are actually oxygen and other dissolved gases escaping from the liquid. At that point, the fish aren't going to be doing very well. So you're going to probably have to either keep your tank a little bit cooler, 72 degrees, 78 degrees, something like that, not 98 degrees. That's not good for most fish. All right, I'm going to repeat these things a little bit for you. This is a short lesson today, but we just need to know some vocab. A solution, by definition, has two parts, the solute and the solvent. Which one of these is the one that gets dissolved? Solute or solvent? Raise your hand if you believe it's the solute. Oh, you all have your hands up. Good. All right. So the solute is what gets dissolved, and the solvent then does the dissolving. Now, there's different types of solvents that you need to be familiar with. The most common solvent is water. It's referred to as an aqueous or aqueous solvent. Is water polar or nonpolar? That's right, it's polar. So things that are polar will dissolve in water. Okay. I'm not sure what the Spanish word for water is. Agua sounds very similar to aqueous or aqueous to me. If that helps you remember water's aqueous, great. Another type of solvent is called a tincture. A tincture, alcohol is the solvent. Now, if your parents drink maybe hard liquor, they might take a cup, pour a little hard liquor in, and put some ice cubes in there. And when the ice cubes melt, they make the drink obviously colder, but you do not get two distinct layers. Instead, you get one uniform mixture because they're what we would say they're miscible, or they're soluble in one another. So alcohol is polar and water is polar. A tincture that you might be familiar with would be if you've ever had your blood drawn. They will rub a little Q-tip on your arm for about a minute, and it's got like a brownish kind of liquid in there. Well, that's tincture of iodine. What they're actually doing is leaving small solid pieces of iodine on your arm. Iodine is quite toxic to the microscopic critters that are on your skin. By waiting a minute then, they let all the critters die. Then they take a second one of those swabs and they start in the middle of your arm and they go in concentric circles. And they're wiping away all of the dead things. And then they can take the needle and draw blood and get your sample without causing any harm to you. So that's where you would probably hear of a tincture of iodine. Next, we have an amalgam. An amalgam is a very unique solvent. The solvent is actually mercury. Now, the only place that I think I've ever actually heard of amalgam would be a dental filling. Maybe your parents had cavities and they had those silver cavities put in. Those are actually a mixture of silver and mercury, and they work very well. They're not very attractive. They last a long time. They're quite inexpensive. A dental amalgam filling will cost you, maybe $75, where if you get a cavity and you have the white porcelain / ceramic ones, it's more of an epoxy, those will probably be about $150. Now, the difference is the mercury ones are going to last longer. If you go to the dentist, if this was your tooth and you had a cavity and this is the filling, they will poke around on top of that when you go in to get your filling. Because what can happen is the filling can actually come up and food can go behind your cavity. And the first time you'll notice is when the roots of your tooth are in trouble. And then you're going to need a root canal. You're going to have to take that whole thing out. That's why they poke around at your fillings. And so they do actually have to be replaced if they get loose. Now, there was an individual named George Decker back in the 1980s when the price of silver went very high. And George Decker went to dentist office in the Chicago area asking them for their old, thrown out amalgam fillings. And what he did with them is he took them home, put them in his kitchen pan, and tried to separate out the mercury from the silver, not realizing that the mercury was more volatile, would evaporate, and he would be inhaling that to get a little bit of silver out of it. George Decker died from this. Excuse me as I lost my earpiece here. And his house had to be destroyed. The government paid to have that done. And many of the neighbors' houses had to be destroyed from the mercury poisoning. So that's a very dangerous thing to do. The last solvent category I want to talk about is organic. If you remember that picture that had the methyl ethyl ketone and the turpentine, all those things you get from Menards, those are organic solvents. They tend to be used on an industrial scale because they can do things that maybe water can't do. They can be, all organic compounds have carbon in them. They can either be polar or non-polar depending on the type organic solvent you're dealing with. Some of them have funny names like benzene or toluene or methyl ethyl ketone or gasoline. These are all examples of organic solvents. One last thing I'll say here about a tincture. Some people drink way too much alcohol. I'm thinking about alcoholics specifically. And when the cause of death oftentimes is cirrhosis of the liver. Now, cirrhosis of the liver, if you were to do an autopsy, you would find the liver has holes all over in it. In essence, what has happened is the alcohol has dissolved the liver. The liver sort of filters out and gets rid of all that bad stuff. And alcohol is not good for you. So what happens is your liver becomes a tincture. It's dissolved. Kind of leave that thought there, let you kind of think about that. So the big idea is know the parts, what a solution are. The solution has two parts, a solute and solvent, and know the difference between aqueous, tincture, and amalgam, and an organic solvent. The definitions, again, we'll just apply them slightly different here. Solution, as mentioned earlier, is always a homogeneous mixture, evenly mixed right down to the particle level. If we take salt water, for example, which one do you think is the solvent? I hope you said water. Okay, and then the salt would be the solute. Do you remember what an alloy is? Did you say a mixture of metals? That's great. Do you remember when we made our brass penny, our golden penny? We took copper from the penny, we coated it with zinc, and we melted the copper and the zinc together, and we made an alloy called brass. Okay? In order to get solid materials to mix, you first have to melt them into liquids and then mix them. Here's a couple more examples of alloys. Bronze is a mixture of copper and tin. Brass is copper and zinc. If you have stainless steel, it probably has some iron in it, along with some chromium and other materials. These are all examples of alloys. As we mentioned earlier, the solvent is a substance that dissolves the solute. So in our example, if we made salt water, salt is the solute, water is the solvent. A couple more definitions for you. I told you today had lots of definitions. If something is soluble, it simply means something will dissolve in something. Okay? So I'm thinking of, you can take a gas and dissolve it in a liquid like oxygen into water. Oxygen is soluble in water. Miscible means two things to dissolve, but they must be in the same state of matter. So two gases or two liquids that form a solution. It means soluble, but it's more specific. So oxygen gas dissolving in water, you would not say they're miscible. If you said you had water dissolved in alcohol, those are miscible because they're in the same state of matter. If you said air is a solution, that would be correct. It is different gases like nitrogen, and oxygen, and carbon dioxide, and argon, all dissolving in one another. So they would be both soluble and miscible. Food coloring and water are miscible. They're both liquid and they dissolve in one another. This chart is to just remind you to think bigger, that a solution is not necessarily just liquids or gases. They can be any states of matter. So I can have a gas dissolved in gas, a gaseous solute, a gaseous solvent, such as air composed of different gases. I can have a liquid solute in a gaseous solvent, like water and air. That's humidity in air. You can have a gas dissolved in a liquid, such as carbonated beverages. And we know that if you take that carbonated beverage on a hot summer day and leave it outside, what happens to the gas dissolved in that hot pop? I hope you said it goes away and the pop goes flat. Remember, for most substances, as you increase the temperature of the solvent, you get more solute dissolved. But for gases, that is not true. We could have a liquid dissolved in a liquid. Vinegar is an example of that. Vinegar is a mixture of acetic acid, between 3 and 5% acetic acid dissolved in water. You can have a solid dissolved in a liquid, such as salt water. You can have liquid dissolved in a solid. We already talked about liquid mercury dissolved in silver, and then that hardens up to make an amalgam. And then finally, you can have a solid mixed in a solid. So you can have sterling silver, which is copper mixed in silver, or lots and lots of other alloys that are examples of solid-solid solutions. Okay, next we want to talk about factors affecting the rates of dissolving. There's a fancy word there, dissolution, but it basically means what makes stuff dissolve. So I'm going to list them here for you. Number one is temperature. Okay, we've already discussed this. As the temperature increases, what happens to the rate of the solute dissolving? Does it get easier or harder to dissolve that salt cube in your ramen noodles? You're correct. It gets much easier. So oftentimes we raise the temperature and wash our clothes in warmer or hot water because it's going to dissolve and get that dirt out, whatever we're trying to get out of our dirty laundry. Okay? Particle size. We've talked about this. If you have a large particle of salt or sugar, or you crush it into small pieces, which one's going to dissolve first? So if we think about it, we've got our solution. We drop in our little cube of sugar, and we don't stir it or do anything. That sugar just sort of sits there for quite some time. If we take a glass stirring rod and crush it into little pieces, all of a sudden some of it starts to dissolve a lot faster. Okay? So as the particle size gets smaller, notice that the surface area right now is only on the edges where it can dissolve. When I crush it, I have much more surface area exposed, so as the size of the particle decreases, the rate of dissolving increases. Finally, you can imagine if I put a glass rod in here and started to stir this, near the top, we have very few, if this is salt molecules dissolved. And at the bottom, it's relatively saturated, meaning that the little places in the solution for that salt to dissolve, they're full. So by mixing it, stirring it up, I can get some of these particles to move throughout the solution. So more mixing definitely increases the rate of reaction. Okay? And finally, what do you think the nature of solvent or solute refers to? If you said that has to do with polarity, you're correct. So a polar substance will dissolve in a polar substance, a polar solvent and a polar solute, and so on. And likewise, nonpolar dissolves nonpolar. If you were to get, let's say, bicycle grease on your hands, you could try to wash it off with soap and water, and that's going to be a little bit difficult. If you just took a spoonful of cooking oil and put on your hands and rub that cooking oil in the grease and take a paper towel, the grease will come off. And the reason for this is oil is nonpolar and grease is nonpolar. Again, a little bit of knowledge of chemistry goes a long ways. So let's review the classes of solutions. We have an aqueous solution, where what is the solvent? Good. You said the solvent is water for an aqueous solution. Okay? Water is sometimes referred to as the universal solvent, which means it can basically dissolve anything and everything. Think about the Grand Canyon made of stone. You know, you give it a few 100,000, a few million years, and water will dissolve right through that. What's an amalgam? What's the solvent? Did you say alcohol? No, that's not right. Yes, mercury. You got it, mercury. Okay? Mercury is a heavy metal. It's toxic to humans, so we don't generally play with mercury. Do you know anything that uses a mercury around your house? A barometer does. So we'll talk about barometers in our gas law units and what barometers do, but they help predict weather is one thing that barometers do. We also talked about you could use mercury to make a dental amalgam or a filling. A tincture, that's the alcohol, is the solvent. And we talked about maybe when you get a little cut, somebody will put a tincture of iodine on the cut. Nowadays, we tend to use different antibiotics and things like that. But tincture of iodine works very well to kill bacteria. And finally, organic solutions. These things contain the element carbon. They can either be polar or non-polar to decide. And there's a few examples of organic solvents for you listed. All right, let's hit a few other definitions. I told you today was not going to be the most exciting in terms of what we're doing. It's just a lot of definitions. Okay? If something is soluble, it means that it dissolves in something. So if it's insoluble, as you might think, insoluble means it will not dissolve in something. Okay? Think about will oil and water, will they dissolve? No, they don't dissolve. They're insoluble. They make two separate layers. Okay? Sand and water are insoluble. Now I can hear you laugh and say, you just said that the Grand Canyon got dissolved by water. Yeah, that's really, really slow. Generally, sand and water are insoluble. Immiscible is kind of like the difference between soluble and miscible, where insoluble won't dissolve, but they can be different states of matter. Immiscible means two gases or two liquids that will not form a solution. So here's your example of water and oil are immiscible and insoluble, where sand and water would be insoluble but not immiscible. Finally, a suspension, if you have a little snow globe or whatever you call those things, a suspension, the particles stay suspended as long as you shake it up, and as soon as you set it down, those particles settle down. That's what a suspension is. The particles are just too large to fit in the interstitial spaces or the spaces between the water molecules. So a suspension could appear uniform while it's being stirred, but settles over time. Think about oil and vinegar dressing. All right, let's think about some mental experiments here. We've got here our first experiment. We have two test tubes, one with cold water and one with hot water. And we're going to add just a single drop of red food coloring into each and see what happens. What do you predict will happen? Okay, they'll both turn red. Can you be more specific? Good. I like that answer better. The hot water will be uniformly red because the water molecules are moving around at the molecular level, making that mix a little bit better, and the cold water won't mix quite as fast. And maybe you know this, maybe you don't. Cold water is denser than warm water, so assuming the food coloring was room temperature, that food color would stay pretty much near the top, and the cold would stay blue until that warms up a little bit. Okay. The food coloring and water are miscible because they mix evenly over time. Let's do another experiment. Okay. This time I have water, and I'm going to pour oil on top of the water, and the oil will just sit on top, and I'll give it a shake, and I can suspend. At this point, I have water in oil, and I have oil in water. So it looks somewhat uniform. And if I just let that sit for a while, notice what's happening is some of the water is returning to the bottom and the oil is going to the top. They are separating back out because these substances are immiscible. They do not mix. Okay, that's what it means to be immiscible. Do you happen to know any ways we can get oil and water to mix and stay mixed? We'll talk a little bit more about emulsifiers and emulsions. There'll be a small video for you to watch. We'll discuss that in relationship to our soap making, and hopefully that'll make sense to you as well. Maybe in your cooking you have oil and water. There's always something you have to add, and I'll let you just sort of think about that. I won't give you the answer right now. All right, let's look at the upper right-hand corner here. I've got a test tube that contains water, hexane. Hexane is an organic solvent, and carbon tetrachloride. And of course, that's an organic solvent because we can see the C in there, CCl4. Now, is there anything you can tell me about this? Okay, we can say that they're immiscible because they are making very distinct lines separating them. That's good. Why are they immiscible? If you said water's polar and carbon tetrachloride must be nonpolar because they don't mix, that's correct. And water's polar and hexane must be also nonpolar. Very good. What do you think would happen if I tried to mix hexane, and that's nonpolar, with carbon tetrachloride, also nonpolar? If you said they'll mix, you're correct. Okay, let's now look at a suspension. We've got some muddy water. Let's go back. So in this one, we've taken water, we added a soil sample, we shook it up to suspend it, and after about a minute, that particulate, the mud, started to settle down. The water wasn't very clear, and after about 5 minutes, the mud had settled to the bottom. That's an example of a suspension. Now, we could determine how much soil we added. This can be done lots of different ways. Dissolved solids can be calculated as a percentage of volume by volume. That might mean 5 milliliters of dirt and 95 milliliters of water. So 5 out of the total 100 would be 5% volume by volume soil and water. It could also be by weight to volume, meaning 5 grams of soil by the volume of the liquid, or it can be weight by weight. I'm not going to ask you this stuff. If you go on in science, you'll realize there's lots of ways to do things. So for right now, we'll kind of walk away and leave this on the side. And I'm just going to skip this whole slide on flocculation. This is a chemical process where you can take muddy water here, might actually refer to soil, or it could also mean sewage. So if you have dirty sewage water, you can do a chemical reaction as described here, and that will cause the sewage water to very rapidly settle to the bottom where it can be skimmed off, and then the sample can be cleaned and reused. All right, the next example I want to talk about is a centrifuge. A centrifuge spins samples very rapidly. The denser material, in this case, we're looking at a sample of blood, will separate out. So when you give blood, they're going to test the blood. They're going to take a little extra vial. They're going to put it in a centrifuge. It's going to spin around. And what they're trying to do is get the red blood cells to sink to the bottom, and the serum, which is less dense, going to the top. This white area in the middle, it would be called the buffy coat. That's the white blood cells. If the white level is too thick, you're probably fighting infection. They don't want your blood. If they spin your sample of your blood and it turns out that you have a very low amount of red blood cells, as shown in vial C, you're probably going to not take your blood because you're what's called anemic. You lack iron. Symptoms of anemia, you will tend to be maybe tired, very pale looking, because iron makes hemoglobin, and that's the molecule that carries oxygen in your body. Sometimes people will develop a craving for ice. That's sort of an indicator that maybe they are anemic and they probably need to have their blood checked, go in and get a blood test. Frequently, it's more common for females to be anemic as they lose blood much more regularly than males do. Things that you can do to increase your iron: you can take an iron supplement if it's recommended by a doctor. You can eat dark leafy green vegetables, and you can get lots and lots of iron from deep leafy green vegetables. Or you can eat red meat. Some people don't want to eat red meat, and that's your choice. All right. Well, as you can see, that sort of is the end of what we needed to get through for this one. And we'll kind of go back and look at our page for the day. So you can review with a short video on water solutions. I've summarized for you there, although it doesn't look right. Solution equals solute plus solvent. Gave you some examples here, reminded you of the difference of aqueous, water, tincture, alcohol, amalgam, mercury. There's a little bit you can watch on what is an emulsion and how do you emulsify substances. There's a kind of cool demonstration of an oil spill cleanup. Now this would be useful if there's a tanker full carrying oil and it were to get a hole in the ocean. You can skim up and suck up some of that water, but you're going to have to use some other technique to get the residual amount, and that's what they're doing with this oil spill powder. And finally, I left a fun little video on how to make slime or gloop. Feel free to do that at home while you're bored. For homework, I've left you an article that says "Don't Sweat the Small Stuff." It has to do with electrolytes. That will be a lesson coming up. So I prefer that you read it and answer the questions that accompany that as well. All right. Hope you have a good day. Day 2 of our journey on e-learning. I'm having some fun, although it's a lot of work. I'm sure it's a lot of work for you too. Best of luck and take care. Stay healthy.